This is question 13 on your recent homework assignment. This is a challenging question, problem, thing, okay? So we're going to go over it right now. So you've got a sphere on an incline. You're going to release the sphere. It's going to from rest. Picture here. So there's your picture. You've got to draw a picture with these things. All right. And so it's released from rest. So, and you also know the height from which it is released from. So h. Right, they show it here in your picture. Let's just see here. So yeah, h. Right, so many meters. It starts off at rest. And yada, yada, yada. You know what h is, and they want to know how fast is it moving when it gets to the bottom of the incline here. So V final. It's also rolling, right? It rolls all the way down the incline. So first, let's look at a similar problem we've done previously, okay? And that would be something sliding without friction down an incline. Right, so real quick, let's look at that question because this is very similar. Right, so, okay, so the solution to that problem we're doing right now is related to this one, which we've done. So here's H, and here's something we're going to just slide with no friction, right? And it starts off at rest, so V naught is 0 meters per second. And it slips down here. We did a lab like this, right? With the little carts, the Hot Wheels, right? And so down here, what is V final? This problem involves conservation of energy, all right? And so that looks like K final plus U final is equal to K naught plus U naught. K is kinetic energy, 1/2 mv squared. It starts off at rest, so K naught is 0. U is gravitational potential energy, mgh. And for this problem, we'll say that U is equal to 0 at the bottom of the incline, 0 joules. Potential energy can be referenced any way you like to make the problem easier to solve. It's only differences that matter in H, there's no absolute H. So if the bottom of the ramp is where H is 0, then U final is 0. Is it all coming back to you now? It's all coming back to you now, isn't it? Because we just did this a few weeks ago. So this tells us that K final 1/2 mv squared is equal to the initial potential energy, because energy is conserved, if we forget about friction, is mgh. Which is why you don't need to worry about mass here. So the m's go away. When you solve this for v, we get that the final velocity at the bottom of the incline is, amazingly, the square root of 2gh. And so there you go. That's how you do the problem here if there's no rolling taking place, all right? The problem we're doing now, there's some rolling that's going on here. That means there's an additional term we're going to add to the problem. Other than that, it's the same as this problem, okay? So again, yeah, it's rolling, right? So then the equation for conservation of energy here becomes, there are two kinds of kinetic energy going on here, right? Because it's both translating and it's rolling, right? So K naught plus U naught. Actually, let me do this the other way around. we'll do the final terms over here. So how about at the bottom here, we have a final kinetic energy, and the final potential energy is equal to K naught plus U naught, okay? So at the bottom down here, it is both translating and it's rolling. So that K final, there are two kinds of K final now. There is good old 1/2 mv squared, but it's also rolling. So it has rotational kinetic energy as well, which is the rotational analog of 1/2 mv squared. Let's think. So that's 1/2. So in angular terms, m, oh wait, that's moment of inertia, I. And instead of v, oh, we've got this omega thing. So now the K final is those two guys added together. 1/2 mv squared plus 1/2 I omega squared. Plus 0, because again, gravitational potential energy at the bottom is 0. All right, at the top, it starts from rest. It's not rolling or translating. So that is 0 as well. So then we have equals mgh. So now we're going to take this expression, okay, and change this omega and the I right here into terms that will get along with these other two terms with the m in them, right? So I'm going to rewrite this over here. Right, so 1/2 mv squared plus 1/2 I omega squared equals mgh. All right, so now it's a little bit of a puzzle thingy we're going to be working here, okay? So first of all, let's take a look at this guy right here. This is moment of inertia. That's the angular equivalent of mass. So guess what? For a sphere, that moment of inertia, I, turns out to be 2/5 mr squared. All right. At this point in this class, we don't need to worry too much about where this comes from. It's the C word, folks, as in calculus. But we can just substitute, all right? And then there's one other thing that's going to help us out here. Recall that if we have something rolling along here, right, so it has its center of mass has a velocity v, and it's rolling along with an angular velocity omega, and this thing has a radius r. The v and the omega are related to each other by this little equation. V is equal to r omega. Okay, we've done this previously. We've talked about this in class and shown where this comes from, and we've used it to solve problems. So now we're going to replace this guy. I know it's a lot of math here, folks, but hey, it's fun, right? Yeah. Some of you think this is fun, I know, or you would be taking more physics next year. It is fun. So now solve this omega for v and r. So if v is r omega, that means that omega is v over r. So now let's put, so we're going to replace the I with this, right? And we're going to replace the omega with this. And check out what happens here, okay? I love what happens, right? So we have 1/2 mv squared plus 1/2. All right, so the I is going to be 2/5 mr squared times omega squared, which is v over r, but that, yeah, so what, v over r, quantity squared. And then that is equal to mgh. I'm running out of room here, so let me make some room over here now. Hold on. I'm going to erase this. You can backtrack anytime you like to see this again, or you could look in your textbook. Okay? So let's make some more room here. So now this becomes 1/2 mv squared. I'm just going to rewrite the whole thing again. Plus 1/2 times 2/5 mr squared times, well, v over r quantity squared is v squared over r squared, and that is equal to mgh. And there go the church bells. Happy Mother's Day, by the way, to all you mothers out there. Now, what are we going to do with this? We're going to cancel a whole ton of stuff, of course. Now, let's see, what can we cancel? How about this 2 can cancel that 2. And then, ooh, check it out. R squared, that makes this r squared go away. Okay, now then let's rewrite this without these terms that we just canceled. So now this becomes 1/2 mv squared plus 1/5 mv squared equals mgh. And I know right now many of you are secretly chuckling to yourselves because guess what else is going to cancel? Yes, that's right. The gosh darn m goes away. I love it when that happens. It's just a thing of beauty, okay? Yeah. Yoink, yoink, yoink. Ugh, the last part. Fractions. Adding fractions. Remember, we're solving for v at the bottom, ultimately, right? So let's see. So 1/2 plus 1/5. Let's think about this. Common denominator. So let's multiply this guy by 5 over 5. And this one by 2 over 2. Okay, so then we have 5/10 v squared plus 2/10 v squared equals gh. All right. And then 5/10 plus 2/10 is 7/10. I should go to a new page here, but I'm not going to. Yeah, so 5/10 and 2/10, definitely 7/10 v squared is equal to gh. So now solving for v, multiply both sides by 10/7 and take the square root. So that's going to give us, finally, in big letters here, v equals the square root of 10/7 gh. That's the answer, okay? This is the important answer. Yes, we can plug in the numbers and get a numeric value for v, right? But this is really, really the answer, because with this expression, you can plug in any values you want for h right here. Okay, and so you have a whole bunch of solutions, basically. Also, let's check this out and compare it to what it was earlier without rolling. If something is just sliding down a hill, right, and we ignore friction, that answer way back was, so this is no rolling. If it's just sliding, the answer was going to be V is the square root of 2GH, okay? And this is whether you drop it and it falls straight down, whether it goes down a curved incline, whether it's a ball on the end of a string swinging through some height h, it applies in a lot of different places. So compare this guy and this guy. This is 2. This is 10/7. That's actually just a little bit less than 2. You wonder, why would that be? Why would this velocity be a little less than this velocity? It's got something to do with the fact that it's rolling, and some of the energy when it gets to the bottom of the hill, in this case, all the energy is energy of translation. In this case, some of that energy is in the rotation. That means the translational energy is going to be a little less. It's the same total energy it had at the beginning. The same potential energy is converted to the same kinetic energy. But if it's rolling, that kinetic energy is split between two parts. Part of it is the translational part, and part of it is the rolling part. So there you go. Problem done. This was a challenging problem. If you've made it this long through the video, good for you, okay? Thank you very much.